following is a discussion and an introduction to sinusoidal modeling. The idea behind sinusoidal modeling is that we can demonstrate or model how it is that real life works for certain scenarios that have a repeating or a cyclical function through sinusoidal modeling. One example of that might be the tides. For example, there's a high tide, then there's a low tide, then there's a high tide, then there's a low tide. It's cyclical in process. Another example is the hours of daylight that we see throughout the year. Typically, we see more daylight during the summer. During summer solstice, June 21st, we have the maximum amount of sunlight. And then it gets less and less until winter. December 21st is the minimum amount of daylight. And it's more extreme at different elevations, different latitudes further away from the equator. So, for example, this is a picture of the number of hours in a day in each of the months throughout the year in Anchorage, Alaska. And you'll notice that if I look at the solstice dates, for example, the 21st of the month, I can look and see that in January there's 6, almost 7 hours of light. In February, there's 9 hours and 40 minutes of light. In March, there's 12 hours and 21 minutes. In April, there's 15 hours and 18 minutes. In May, there's almost 18 hours. In June, there's 19 and a third hours of sunlight. And then it starts trickling back down again. We should be able to create a model for this using a sinusoidal graph that starts small, builds up, then goes small again. Taking this data, each of you should, on your graph paper, write these points of data as coordinates, 1, 653. But we don't want to use 653. Convert that to a decimal. That should be almost 7. It's going to be 6 and 53 sixtieths. We should round it to the nearest 10th place. So 6 and 53 sixtieths is 0.88. So that would be 6.9. 9 and 40 sixtieths would be 9 and 2/3 or 9.7. So these coordinates can then be plotted, and you might want to pause the video now to allow everyone to copy these points down and to create a graph. We expect the y-axis, which is the hours of daylight, to go all the way up to about 20. And the x-axis is the months, January, February, March, April by number. Take a moment, please, to create this graph and plot these points. Pause the video. Having plotted the points, you should create something like this. And notice that it looks somewhat like a sine or a cosine curve, or a portion of it. But it terminates at a lowest point, which is in December. What happens to our y-intercept over here? Well, since it's cyclical, it should continue back to the left. So month 0 is really the same value as month 12. And month 13 is the same value as month 1, because it's cyclical or sinusoidal. Now, I'd like to build the equation for this particular model. So looking at this picture, we have to identify the critical values. This top point, the maximum point, can be thought of as having an x of the maximum and a y of the maximum point. It's got an x value and a y value. Remember that the x refers to the maximum values x, not the biggest x value, because that would be here. And the y refers to the maximum's y value, which does in fact match the biggest y value. In this case, that coordinate would be 6, 19.4. Similarly, I have a minimum point, where the x minimum refers to the smallest x value and the y minimum refers to the smallest y value. And in this case, it would be 0, 5.5. To create an equation, I need my A. A is, of course, the amplitude from the center line. How high is it to the maximum? We can find that by taking the maximum y value minus the maximum y minus the minimum y. That gap is twice A. So if I divide that by 2, I get the actual A above and below the line. Now I need B. B is where my midline is. This is what the whole function has been shifted up as a new central axis. And the way I can do that is average the max and the min, bringing them together to find the midpoint line So this suggests that at 12.45 is the midpoint. And if I go 6.95 up from that, I reach my maximum, 19.4. And if I go 6.95 below that, I reach my minimum of 5.5. There's also a moment for discussion. Take this now, talk to your groups. What does it mean that this has moved up to 12.45? In real life terms, what does that describe? In real life terms, what does the 6.95 as A describe? Take a moment to discuss and pause the movie. I trust that you've had a discussion about this 12.45, and what it means is that throughout the year, on average, we have more hours of daylight than we do of darkness. It's not an even 12-hour split each way. It's 12.45, almost 12 and a half hours of light, and thus about 11 and a half hours of darkness. And the swing is this 7 hours almost. In other words, in the middle of summer, we get almost 7 extra hours of daylight in Alaska and lose almost 7 hours of that time in daylight in the winter. So let's continue. We've got our A, we've got our B. Now we want to find our period. Well, we know that a low point to a high point takes up half the period, right? Low to high, high back to low. This is half the period. So if I want to find the full period, I just multiply double of the difference between the biggest point's x value and the littlest point's x value. Take the difference between these two x's and multiply by 2. I can then find omega by recognizing 2 pi over the period gives me omega of pi over 6. Phi over omega is my horizontal shift. And what we want to think about is where my sine curve starts. It starts right here. So I need to figure out what I have to move from my normal location, my axis, to get to that new starting point. And it turns out it's going to be the minimum value plus exactly 1/4 of the period. Always, always, always. Since that's 1/4 of the period, if I add that to my x min, 0 plus 12 divided by 4 is 3. And that makes sense. In March is when it begins working its way up to a maximum again. By taking these values we've found for A, B, omega, and phi over omega, we can create our equation. We know that this is our standard form of the equation, y equals A times sine. We're assuming sine with a positive coefficient, omega parentheses x minus phi over omega. And this x could be theta just as easily. It's really interchangeable. Some books talk about using x when we're talking about radians and theta when we're talking about degrees. I don't personally subscribe to that. I find them interchangeable. This is our phase shift. This is our vertical shift. So we can think about it as bringing in each of these values where they belong. And this is our equation to describe the hours of sunlight in Anchorage, Alaska per month, where X is the month of the year. Now, your activity for the day is to do the same thing for Mill Valley, to take that equation and create one for Mill Valley. Here's the data. Go. Just kidding. Let's highlight it for you at least. Give you an opportunity there. We're going to pass out the worksheet that lets you do this. Work at your tables to find the equation for Mill Valley.